Welcome. I'm Liz Taylor, ocean explorer, naturalist, and entrepreneur.
And I'm Sylvia Earle, an ocean elder, oceanographer, explorer at National Geographic, and founder of Mission Blue.
This is our show, Dive In, where we host informal and open conversations with the ocean community on topics of wonder and interest. And I am going to share the screen now.
I wonder.
It is a wonder when it
It's
works.
of great interest.
All right, great. You're gonna pull. Oops. Oh no. Come on. Come over here, buddy.
Tug it over.
Tug it over.
Ah, there we are. And now the world is blue.
We have to remind everyone of that every time, even though most of our audience knows that. Let's see. We're going to have Q&A towards the end of the program as usual. And throughout the conversation, there will be some links and things in the chat to join in on. And today we're going to be joined by our dear friend and collaborator, Samantha Joye. And she knows well that the big blue back of the planet is full of all the little important stuff.
Life.
Every spoonful.
There she is, Mandy Joye.
Mandy, can you turn on your video and microphone?
Actually, it's Dr. Samantha Joye. But the fish know her, and the microbes know her as Mandy.
That's right.
Right. and Mandy's lab there at the University of Georgia is just world renowned for teaching everyone about microbes in the ocean.
There's that word, biogeochemical. I mean, we should learn that when we learn our alphabet because it is so important. I mean, it's vital to understanding the nature of the world itself.
It really is. And these little microbes in the ocean, there are more microbes in the ocean than there are stars in the universe. And that's a statistic that always blows me away. But when you think about what these microbes do, they're little engines, and they carry out all kinds of processes that make Earth a livable planet. And without these microbes, these little super tiny superheroes, the Earth would be a very, very different place.
Yeah, most people think of microbes, otherwise known as, quotes, germs, as bad guys, but we couldn't live without them. And most of them, if we think of them as good or bad, are really on the good side of the ledger. There are only a relatively small number that give us a hard time.
Absolutely. I mean, and the ones who are pathogenic are typically not so bad. You know, some of them are true pathogens, but most of them just turn ugly when they have a bad day. But I want to share with you all today a little bit about the Gulf of Mexico, which, Sylvia, I know is one of your favorite places, and it certainly is one of my favorite places in the world. And the Gulf is an incredible ecosystem that is driven by oil and gas seepage on the seafloor. And everybody remembers the Deepwater Horizon Oil Spill that happened in the Gulf of Mexico back in 2010. But there's also a lot of natural oil and gas seepage that occurs in the Gulf. And the picture up on the top left shows all the known oil and gas seeps in the system. There's about 20,000 or so documented areas of seepage, and there's about 2,000 active seeps that have oil and gas discharging from the seabed, like is shown in the bottom image there.
And they seem to be very dense with life. You see all these little critters kind of.
Absolutely. There's all kinds of vertebrates and invertebrates as well as microbes that dominate these systems. And, you know, cold seeps were discovered shortly before hydrothermal vents, although hydrothermal vents got all the billing for chemosynthetic ecosystems. But it's really cold seeps where this extreme life in the deep sea that was independent, you know, from the sun for the most part, was discovered. And the Gulf of Mexico was that place, and we've been working to sort of understand the dynamics of this extreme life ever since.
That's been going on for a very long time. The oil and gas extraction only began seriously sort of around the middle of the 20th century, and
Yep.
Think of all the gazillions of years that preceded that, where these systems operated in a peaceful way, in a way that was not disruptive, but along come humankind, not so kind. We have unwittingly unleashed some powerful agents of change, and you've been right in the thick of it, Mandy, since the beginning of your career. I think your interest in microbes has really been so important, a better understanding of both the natural and the modified activity out there in the Gulf.
Yeah, and I one of the most fascinating aspects of this, from my perspective, is that we know that there's a tremendous amount of oil and gas seepage in the Gulf of Mexico and in other similar systems. The Gulf of Cadiz on the west coast of the US, there's oil seeps around Santa Barbara and LA. There's gas seeps all across continental margins on the east coast of the US to the northwestern US. It's everywhere.
Iceland.
Yeah, I mean, in the Arctic, it's all over. It's ubiquitous, but you don't see tar balls washing up on the beaches, right? And the oceans are a really small source of methane to the atmosphere, and that's all thanks to microbes, because the flux of hydrocarbons out of the system is matched by the consumption of those hydrocarbons by microorganisms. And it's a very delicate balance, just like the earth in general is balanced. This part of ocean biogeochemical cycles, the input and the microbial consumption are very tightly tuned. And when you increase that consumption, like what happened in the Deepwater Horizon oil spill, it overwhelms the capacity of that microbial biofilter to consume that oil and gas.
Oh, I like that. It's microbial biofilter. It means
yeah,
capturing the methane and turning it and keeping it in the ocean rather than letting it escape into the atmosphere.
Yeah, and essentially they're feeding the fish. These microbes make biomass, and then they are consumed by zooplankton and then small fish and then large fish. And in lakes where they're much smaller systems and easier to track, it's been shown that these methane eating microbes, they can account for 20 or 30, sometimes even 40% of the food that the fish are consuming in these lakes in the summer when the methane is fluxing out of the bottom. And in the ocean, we saw that during the Deepwater Horizon Oil Spill, that the oil and gas was really feeding the higher trophic levels. But on the bottom, there's just some spectacular habitats. We went to see some of them when we were out there in 2016 filming Blue Planet 2, and I'll show some slides from that later. But there are brine pools and brine volcanoes and gas hydrates and areas where brine and hydrate are sort of commingling. Just incredibly otherworldly looking habitats that are there's hundreds and thousands of these habitats in the Gulf of Mexico, and we've explored maybe 30 or 40. So there's lots left.
A lot to be done. I see that you've got the one here. It looks like some little bubbles are coming up from the seabed. What's going on there?
They're burping.
So that's an area of massive methane discharge, and it's hard to see in the figure. But when you have methane discharge, there's actually two ways that methane can be sort of contained in the system and keep from being discharged to the atmosphere. One is from biological organisms, these methanotrophic bacteria, these biofilters that eat the methane and feed higher trophic levels. There's also some bacteria that eat methane, and that they're actually archaea, a different flavor of microorganism, but they live in the sediments. And what they do is they generate a lot of alkalinity. So and this is where the biogeochemistry comes in. The biology generates a chemical signature that creates a geological system. So this is actually, if you could hop out of your submarine and walk around on the bottom where those gas flares are coming out of the bottom, it's actually hard substrate. It's authigenic carbonate. And there's just kilometers and kilometers and kilometers of this authigenic carbonate in the Gulf of Mexico and other systems where hydrocarbons are discharged. And those carbonates are long-term waste stations for that carbon, because it's very stable once it's in the solid phase. So about half the carbon, half of the hydrocarbons that come up, they get turned into autogenic carbonate pavement. The other half of it goes into the water column and feeds the pelagic microorganisms, and that can actually feed, fish ultimately.
Does it kind of lay down in layers over time? Is that what happens with it? Is that how it takes over?
It's interesting. I mean, there's lots of different varieties of carbonate. There's carbonate pavement, which is what this is. Sometimes when you have gas hydrates, which is the panel opposite in fact, if you go to the next slide, I think it's a big gas hydrate mound. Oh, sorry, it's one more. You can go forward one more. We'll come back to that.
I want to see. Oh, we want to see all these little critters. Huh?
So these critters are all the animals that live off the microbes in the chemosynthetic habitat. So these are tube worms, mussels and clams, and cold water corals. And the corals, there's a sequence of large animals that inhabit these seep systems. And when there's really high flow of hydrocarbons, you get mussels and clams and tube worms. And once the hydrocarbon flow has slowed down and you don't have toxins like hydrogen sulfide being produced, but you've got lots of hard substrate, the corals move in. And the cold water coral habitats are sort of like the parallel on land would be just a climax forest, a fully mature hardwood forest that has, evolved over hundreds of years. And that's what these corals represent, is a fully evolved community. But the shift between these high flux and low flux regime is very well documented in the Gulf of Mexico and elsewhere. But these cold water coral communities are hugely important in the fishery in the Gulf of Mexico. Shrimp and fish use these as habitat, and these corals, some of them occur in mesophotic areas, so where there's light, but the vast majority are aphotic. In fact, half of the world's coral reefs are deepwater coral reefs that are not in the photic zone. So not your typical reefs that you go diving on in the Caribbean or in the tropical Pacific, but these you have to have a submarine to dive on.
That's right.
But they're everywhere. I mean,
cool.
they're all over the place.
Yeah.
So, Mandy, a big idea. You see in textbooks, and you hear it all the time, that life on Earth, animals at least, exist because of photosynthesis. Thank you, little green guys, for capturing carbon dioxide and using water in combination with chlorophyll and generate oxygen and generate food. And yet, what you're describing is a process where food is generated in the absence of light.
Yes.
And stores carbon by going through the food chain in the same way that using photosynthesis develops food that is ultimately stored as carbon, whether in the soil or in the deep sea, when these creatures that munch on their various forms of groceries, when they give it up and die. But it's only really in very recent times that chemosynthesis, generating food in the absence of light, is getting some notice. How much, well, it's hard to say, isn't it? Most of life on Earth lives in the dark because the light only penetrates a short distance relative to the overall depth of the ocean.
Yeah. So I think that's a really good point and an important one, because we can constrain like how much of this sort of, well, we can sort of constrain how much geothermal energy there is coming into hydrothermal and coal seep environments and how much carbon fixation it could support. And it's a small fraction of that, due to photosynthesis. However, these places that are up on the screen, deep sea chemosynthetic oases, many of these processes that happen at these sites, whether it's methane oxidation or sulfide oxidation or ammonia oxidation, they happen throughout the ocean water column, not just at cold seeps. You don't get tube worms. Tube worms happen at cold seeps.
Right.
But there are other chemosynthetic processes that happen throughout the oceanic water column, and it's very, very poorly constrained. There's only 2 long-term data sets, one from the Bermuda Atlantic time series and one from the Hawaii Ocean time series. And obviously one in the Atlantic, one in the Pacific, very different results. But what they show is that this, what I call dark carbon fixation, so carbon fixation without light, it can be as much as 25% of photosynthetic carbon production. And it seems to be changing as the ocean is heating up, which is really interesting. And we don't know why. So this is something that we are actively pursuing, trying to understand the relative importance of this dark carbon and how dark carbon fixation, how and why the rates seem to be increasing as the oceans stratify and warm up, because that has a lot of fundamental implications for food webs in the oceans, trophic carbon flow. That's something we need to have a fundamental understanding of that, and we don't.
I'm so glad we have those time series, both in the Atlantic and over in Hawaii, as those baselines, that we can really kind of monitor that change over time and get a much better idea of what's going on with these systems.
Yeah, and it's, those data sets are invaluable. I mean, there was a paper published in Bioscience by John Magnuson in 1990 called The Invisible Present. And this paper was about the importance of time series data sets in ocean science and terrestrial ecology. And what the point he makes in the paper is a very elegant one. And it said, if you have static measurements that just happen stochastically, you go out once and then 8 years later you go out again, and then 20 years later you go out again, you're never going to be able to actually document change. And the US has this program called the Long-Term Ecological Research Program that's funded by the National Science Foundation, and they fund a lot of long-term studies, mainly in terrestrial ecosystems. We don't have, other than HOTS, we don't have that in the open ocean. And we know that different parts of the ocean are dramatically different. The Atlantic and the Pacific are totally different. Germany funds a station in the Arctic called the Fram Observatory that's up in the Fram Strait in the Arctic. And there's one down in Antarctica that's funded through the LTER program and it's the Science and Technology Center as well, the Palmer Station program. But there's nothing in the Gulf of Mexico, and we don't have anything comparable in sort of the Eastern Arctic. When we need that in the Eastern and the Western Arctic. So there's a lot of long-term monitoring that needs to be done.
Yeah, definitely.
Yeah. Here we go.
So I had in the title of the talk about geobiological engines, and I've mentioned this a little bit before. These microbes that inhabit every imaginable habitat on Earth, they're just tremendously abundant. In a milliliter of seawater, there's anywhere from 1 million to 200 million microbes, just in a speck of water.
Yeah, just a
yeah, I mean, their abundance is really phenomenal. But what's even more sort of mind-boggling is that these really are the little nanomachines that keep Earth habitable. Picoplankton in the ocean produce 50 to 60% of oxygen on Earth. There are microbes in the ocean that serve as sort of kidney functions. They detoxify and decontaminate, whether it's oil or hydrogen sulfide or excess nutrients like nitrate. These organisms basically they do what's called they mediate redox processes. So they breathe electron acceptors, like we breathe oxygen. They breathe sulfate, they breathe nitrate, some of them breathe oxygen. They can breathe lots of different substrates, and then they get an energy source, like we eat, carbs or fruit, and that's our energy source. But these microbes take, methane or ammonia or oil or alkanes or just part of a tree that's floated into the ocean. They can break all this stuff down into the mineral components, the initial inorganic building blocks like CO2 and ammonia and phosphate. But along the way, they make all these intermediates that feed their friends. So it's a food web that's driven by microbes that respire and ferment, and they live in particles. They live in the open ocean. But in all ecosystems, these microbes carry out critical functions that just underpin the basic working of nature. And in the ocean, there's lots of different habitats that we can study these processes, but these deep sea extreme environments, they are like supercharged in terms of the rates of activity. So they're fantastic places to explore, look for new pathways and processes and new organisms, because there's lots and lots of energy available. So the communities are really diverse.
And all creatures in the ocean, like all humans, have their own personal microbiomes.
That's right.
Yeah.
That's right.
So it's part of what makes each fish different from every other individual fish. Every tuna is different from every other, partly because they have different biomes.
Yeah.
Similar, but different, unique.
Yeah, and I think we've talked about it, Sylvia, that, the microbiome in microbes talk to each other using chemical compounds, little or signaling molecules, and the fact that every organism has a microbiome means potentially that every organism could be chemically conversing with each other in ways that we just don't have a clue about. And that really fascinates me, because if you've got it's clear from the few studies that have been done in the ocean looking at animal microbiomes, but certainly the human microbiome, your microbiome when you're quote unquote healthy is very different from your microbiome when you're sick. And you can actually sense and gauge the relative health of by looking at their microbiome. And the same thing goes for animals in the ocean. So I think microbiome science is in its infancy. But it's incredibly powerful to think about the ways that you could use that information as a diagnostic, as a sentinel even for problems and change. And we need to do that, because if we could figure out how to, read this microbial information, then we can have a better understanding of what regulates primary production in the ocean, how the ocean is performing its kidney liver function, what is the role of biodiversity, is how we know we're in an extinction crisis right now across the earth, and that is certainly true in the ocean. And what's going to happen to the system when biodiversity is reduced by wherever we land after this situation we're in right now. One of the most interesting drugs, I read a lot of the biotech literature, and one of the most interesting new drugs that's out there, it treats glioblastoma, really, really dangerous and incurable brain tumor. It was recovered from a microorganism at the bottom of the Marianas Trench. And it makes this chemical compound to keep its, to kill its neighbors off so that it could eat all the food. But there's there are all kinds of resources that are in the deep sea waiting to be discovered. And the ocean plays a huge role as a climate capacitor in both absorbing heat and absorbing carbon dioxide. So there's lots that we need to do. But understanding microbes in the ocean is key.
It's really a source, I think, for so much biopharmaceutical research, but we've got to take care of these systems so that they're there for us to explore, not just exploit.
Well, the deep sea mining issue, Mandy, gives me nightmares, because
beyond nightmares.
There's a library that we're just tearing through for short-term, small return with maximum damage. I really makes my hair stand on end.
Me too. And it feels like it's the oil and gas industry on repeat, right? It's when we're going to talk about the Macondo blowout a little bit, and resources, biotech resources, fundamental information that could advance, the human enterprise. It's all there at these in the Gulf of Mexico, and these hydrothermal systems where they want to do deep sea mining. And we didn't really learn when it came to deep sea drilling. I think it was known at the time, but we, the public, didn't really understand the implications of, essentially sucking fossil fuels out of the ground with a straw, which is what we're doing when we drill, into these reservoirs and pull, allow the overpressure to drive the oil and gas out. When you think about climate change, we talked in the very beginning about how the natural cycle of oil and gas, the inputs are tightly balanced with the microbial capacity to consume that oil and gas. And that's why for hundreds of millions of years, absent, ice ages, which are a whole nother thing we could talk about, and mass extinction events that were driven by volcanism or meteor impacts, Earth's climate has been pretty darn steady. And, aside from those perturbations, and until you get to the Anthropocene. And that's because we have sort of bypassed this filter and we're injecting this fossil CO2 straight in the atmosphere. Now with deep sea mining, it's full steam ahead. But if I don't want to get to 20 years from now and realize, oh God, that was really short-sighted. I mean, I think this is one thing that we have got to get ahead of, and we've got to really understand the risk before things, get out of hand, because we've had major oil spills about every 7 to 10 years since, the 1970s, even the 1960s, the Torrey Canyon spill. But they don't have to be inevitable. I'm a firm believer of leave it in the ground, because I don't think we can afford to recover more oil and gas. We've already interfered with the climate enough to start reversing the trend. But the Deepwater Horizon was just an eye-opening experience, because it was all about greed, right? It was all about greed, because they were running behind and they made some shortcuts, and a platform blew up. 11 men died, and an ecosystem was forever changed. Yeah. And when you look at the consequences of that action, there weren't a whole lot of consequences. Nobody went to jail. And the fine sounds really big, tens of billions of dollars. But in terms of the ecological costs in the system and the personal cost to the people around the Gulf system and the people who are still sick from dispersant exposure, you can't put a price tag on that. No, and just and for comparison, when you look at natural, this is a map on the right of the oil distribution on June the 5th, which was the peak oil coverage in the system. And the things that I want you to sort of focus on here are the fact that this one hole in the ground, the Macondo wellhead, was injecting some 70,000 barrels of oil per day as a point source. And it was located at that red cross on the figure on the right. All the natural seeps in the Gulf of Mexico, all of them, 5,000 barrels of oil per day. So order of magnitude increase, and it lasted for 84 days. And I don't think we'll ever really have a real solid idea of how much oil and gas was released, because the discharge rate was not determined frequently and sufficiently for a lot of people's satisfaction. But what we do know is that it was just a gigantic perturbation that had impacts from top to bottom in the Gulf system.
Which would not have occurred naturally. It took our intervention.
Yes.
Drill down, 2 miles? At the bottom of the ocean to get to where this, under high pressure, this reservoir.
Well, that's one of the things. I mean, oil naturally wants to come to the surface, and then when you get that little, it's like bursting an abscess or something. You like pop it in there, and then it, and it wants to come to the surface all at once.
Yeah, and it's very, very hot.
Yeah. Oh yeah, very hot, and so it ends up. There were all kinds of crazy things that happened after this spill started. one of which they weren't even able to determine the flow rate in the beginning. It was in June before they determined the flow rate. So by then, think of the overpressure that had been released.
Right.
In 6 weeks of overpressure had been released. So it's very likely that the discharge was much higher in the initial weeks of the spill. But we know that there was oil in the deep water, there was oil throughout the water column, there were all these little slicks that you could see in the surface. But the best estimates we have was that 50% of the oil and all the gas that was discharged stayed below the surface, so would never have been accounted for if it hadn't been for those of us who were looking for signatures in the deep water.
Right.
And that those data played a role in sort of refining the oil budget. And improving the numbers of discharge. And those numbers are obviously important in terms of assessing ecological impact.
Right. And then, the use of the dispersants on the oil that did come to the surface, it was just it just kind of was insult to injury.
Yeah.
Can you explain a little bit about how that changes the character of the oil and makes it kind of harder to cope with for the natural systems?
Sure. Maybe go to the next slide. I think there's a dispersant slide. This is not it yet, but I'll talk about it and then we can talk about the first responders. Okay. So these dispersants are chemicals that are essentially surfactants. They're like soaps. And what they do is they surround oil droplets and they pull the oil apart and they make the oil dissolve into the water column. So they break up surface slicks and they push the oil into the aqueous phase from the organic phase. And that is perceived to be a very positive thing because there's no more oil slicks on the surface. But in reality, all you're doing is moving the oil from a visible slick that you can see to an invisible emulsion that you can't track. And the oil still gets to beaches. It's just mixed with dispersant and it's going into the beaches, but it's not a thick tarry oil slick. It's dissolved oil. And it makes it impossible to track it through the system. And that's the goal isn't to make it impossible to track. The goal is to break down surface slicks so that you don't have these big oily biofilms and films on the surface. So it's very tempting to say, oh, all the oil slicks are gone, but they're not gone. They're just invisible. And more importantly, it only works to put the oil into solution if there are organisms in there that are going to break it down, right? And it turns out that dispersants, at least some components of the dispersants, actually interfere with the natural microbial population's ability to break that oil down. And so that means that you've really added insult to injury. So you've taken this slick, you've turned it into this, and you're not biodegrading it. And that's a big problem. So
think about the fish, the jellies, all those other creatures that live in the water column. They can kind of stay under the slick if the oil stays at the surface.
Right.
But once the dispersants are applied, it just fills the water column with toxins that they cannot avoid. You're taking a bath, literally. Yeah. Their gills that are ultra sensitive, of course, are just,
overwhelmed. Just like the microbes are overwhelmed, these animals are overwhelmed too.
Yeah. And what's even worse is that we know from just various studies that have been done with these surfactants, for animals with skin, it opens up the pores in your skin. So if there is oil around and you're basically getting more of a dose of toxin with dispersants as opposed to without dispersants. And what we saw in the system, in the Gulf system, was a really tremendous impact of these dispersants across trophic levels for different reasons. But this figure shows you primary production and carbon flow. And in the figure on the what you can see is that after 2010, there was a substantial drop in primary production rates over the system impacted by the oil spill. And that drop lasted for 3 years.
Wow.
And it rebounded a bit in the 4th year and was back up by the 5th year. But imagine what that does to the fishery.
Yeah.
If the basic input to the food web through phytoplankton, which feeds zooplankton, which feeds small fish, which feed big, if the phytoplankton have decreased their activity for 3 years, then everything else suffers too.
It's landslide.
Yeah.
And so
Fish.
one of the impacts of this, and this is really a shocking impact. This is Tracy Sutton, my colleague at Nova Southeastern University in Miami. He found that the numbers of lanternfish, which are key prey across trophic levels, decreased by 4% in the Gulf system since the oil spill. And that has just tremendous implications for all kinds of animals. Can you switch to the next slide?
Yeah, sure.
Because all of these animals, from beaked whales to spotted dolphins to frigate birds to bluefin tuna to sperm whales, all of these animals depend on lanternfish.
Well,
and
they depend
84% decline is huge.
on that deep scattering layer, that layer of life that migrates vertically. It includes little squid, which are obviously caught in this catastrophe, and lanternfish. Lanternfish are among the most abundant creatures on the planet, but they are also, as you point out, the source of food for so many creatures that we see at the surface or know are just like the tunas, but that's where they get their groceries.
Yeah,
they make
Absolutely.
they dive down to where the action is, and it's been hidden from view, not unknown to scientists, but unknown generally speaking until recent times. And now that area, clearly vulnerable to changing chemistry, to the new toxins we're adding, but also it's now being targeted for fishing. So lanternfish, it's the new deep gold, if you will.
Yeah.
A number of nations are gearing up big time to tap into this area that is vital to the health of the ocean, to the climate.
Yeah, I mean, the mesopelagic is so underrated and not well understood and poorly documented. And again, it's this resource that is so vulnerable to exploitation, and people just don't understand that A, it's even there, and B, why it matters.
And it's not just there for us to take. That's part of what holds the planet steady. It's critical anchor in the carbon cycle.
When you think of something like lanternfish and other small animals like that, when they do those vertical migrations, they're actually mixing a tremendous amount of water.
That's right.
As well, so it's really kind of facilitating the whole cycle, bringing nutrients and carbon and in the sequestering process.
All these gazillions of little fins going flip, flip, flip.
Yeah, they're like,
yeah.
That's a lot of a water movement right there.
It is.
No, it makes a huge difference. You want to move on and talk about the dispersants? So here's a slide that shows you what I was saying before about these dispersants. So these dispersants, they take the solid oil that's on the left side of that right image, or the right side of the right image, and they turn it into this dissolved oil.
Yeah.
If you go to the next one, there were a lot of consequences of dispersant addition, aside from the fact that these chemicals are toxic. And one of the most surprising things was that when you generated all this dispersed oil and you had microbes come in there that were trying to break this stuff down, it turns out they like to eat the dispersant more than they like to eat the oil. And what happened was it resulted in a lot of oil getting transferred down to the bottom by this sort of microbial throughfare that we called microbial oil snow. And this was something that was just not appreciated at all. It was not factored into the response planning. And it turned out that somewhere between 5 to 20% of the oil that was discharged ended up sedimenting back down to the bottom. And if you go to the next slide, I've got some pictures that sort of show how this worked. So we saw a lot of examples of these big streamers in the water. And then when we were taking cores around the wellhead, we could see these really thick layers So in this part of the Gulf of Mexico, you might get a millimeter of sedimentation a year, maybe. You certainly don't get 11 centimeters
11, no, it's huge.
in a year. And we were getting, you know, anywhere from 4 to 15 centimeters everywhere around the wellhead.
Thank you, dispersants, for accelerating the buildup.
Sedimentation. Yep.
And it's filled with toxins.
Oh yeah, totally filled with toxins. And the microbes in these layers are just not happy at all. I mean, they're not doing their normal thing that they do in sediments. And if you switch to one more, we can see the sort of the map of impact. And the other thing that had a huge impact on sedimentation was the burning that happened. They did these surface burns, and these were awful because there were inevitably animals trapped in these burn corrals, and, you know, sea turtles especially. It was just awful. And there were just fires everywhere. I mean, it was, I took a reporter from the New York Times out there, Justin Gillis, and he wrote a piece in the New York Times called "The Ocean is on Fire." And, you know, who would ever think you would see those words publicly written anywhere? But I mean, just everywhere you could see at night, it was just like the surface of the water was on fire.
So Mandy, you're a scientist. You call it the way you see it. You're not a politician, but you got caught in the crosshairs of politics because you just said, as a scientist,
exactly what was happening.
You got to see, here's the evidence. I'm just telling you what I see and measure and document. We're not making this stuff up. And I really felt for you because you got a lot of grief, and were really, your whole position as a scientist was under fire from those who did not want to hear the truth.
Yeah, I remember, you know, we talked so much during that entire period when I was working with the Deepwater Horizon Study Group, and you were out there like getting the samples, and it was horrendous.
Even from NOAA.
Yeah, nobody wanted to really face up to what was going on, and you think about that oily snow coming down, and then what about all the benthic animals, the bigger animals as well, that were coated in that stuff?
It was crazy. And, you know, it wasn't just the government, you know, other scientists were also terrible. And I remember, you know, there were a lot of people that were out there who really wanted to make a name for themselves through this oil spill. And more than one person said to me, well, you know, you're only doing this to get your name in the newspaper. You're only doing this to get, you know, interviewed. And that just makes me chuckle because, you know, I'm an introvert. I don't like the attention. Sometimes you see things and you can't just sit there and look the other way because it's outrageous, and you have to do the right thing. And what I find satisfying is that all of the issues that we raised in the first few weeks of Deepwater Horizon, the issue with dispersants and the potential negative impact on oil degradation, the fact that there was going to be oil sedimentation to the bottom, that this was you know, fairly easy to predict, the fact that a lot of the oil and probably all the gas was going to be underwater and we weren't going to be able to track it. All of those things were correct. They were proved. I was proven right in the end. But good grief. I mean, I had to disconnect my phone. Yeah, I had to get big, you know, movie star glasses and a hat. I couldn't go anywhere without being harassed, being threatened. It was terrible.
Yeah.
But we ended up, you know, documenting things like deepwater corals getting damaged by the oil, and what happened to these animals. You know, these animals grow a centimeter per year, and an animal that's and they're filter feeders.
Yeah.
And an animal that's, you know, 2 meters tall is 600 years old, and they aren't going to recover overnight. And we had a long-term program that was monitoring coral health, and we found that, you know, at the end of our 10-year assessment, they were still declining. And we don't know now because nobody's monitoring them anymore. No. And so, you know, I think one of the things that Deepwater Horizon did is it showed us that the natural resource damage assessment in a year. You can't even do a natural resource damage assessment in 5 years, but there's a lot of pressure to do it fast because you want to get a settlement. You want it to be done with. But if we don't even know what the impacts are, how are we supposed to do a settlement that we can sleep with at night? I mean, I'll never understand it. And the corals are just a hallmark example. And the fishery too, the mesopelagic fishery, that was not clear after a year that the fishery had crashed and wasn't going to rebound. So a lot of the decisions that were made in terms of the settlement were based on incomplete information. And that information has come out to some degree since then. And I think everybody's aware that, you know, the next time this happens, we've got to be much more judicious in terms of the insisting on longer timescales for these sorts of damage assessments.
But now we should jump over to something that's a little bit more upbeat, yeah?
Yeah.
But it's a great opportunity that you had to go back and look at some of these areas, but to directly get down and view them.
Oh, those brine pools, the deep lakes within the ocean. It's something that's hard to imagine until you actually get down there and see it. And I love being there with you, Mandy.
It was so fantastic to be able to share these deep sea wonderlands with you, Sylvia. I mean, this is the first place I ever dove to. The NR1 brine pool was my first submersible dive back in 1994. And it's just an amazing, amazing place.
I was able to visit during the Sustainable Seas expeditions using the little deep worker landing at the edge of one of those brine pools. How many are there? There are quite a few.
Oh, I would be hesitant to put a number on it. I bet there's hundreds out there. And I don't think we even have them all mapped at this point.
Right.
No, not at all.
But having a little bubble, Liz has her fingerprints on the Deep Rover, as do I. The system that, if you go back one, there you are in the Deep Rover 2, right at the edge where the mussels are thriving. And they go right up to the edge, but they don't go into the brine pool itself.
Can you tell us about what happens if you go into the brine pool?
Well, we took the Alvin into a brine pool once, and it seemed like the right thing to do at the time. But when we came back up top, no one was excited, because it turned out that every one of these brines is chemically distinct. And we had dove the Alvin into was not pH neutral. It was a little bit on the acidic side. And a lot of the bolts were just black with sulfide. It was a mess. We got tagged essentially cleaning the submarine. We were up all night cleaning the submarine. But it was amazing because we didn't get down very far because it's a brine and it's dense. But it was like going, flying through the asteroid belt in the Star Trek Enterprise, massive precipitates of barite, all these pickled invertebrates, sea cucumbers and eels and all kinds of animals that were just pickled and floating. There's all kinds of stuff in that brine. And it was one of the most microbially dense brines that we've ever seen. This was the AC601 brine that's in Alaminos Canyon in about 3,300 meters of water in the Gulf of Mexico. And it was a spectacular, 15 minutes that we were able to be under the surface. And, I've always wanted to go back and drop a camera system into these brines because, nobody knows what's in there. I mean, that's the only video everybody has of what these things are like, is that 15 minutes that we went in there. So I'm really hoping that someday we can go out there with a camera system and, from the ROV or submersible drop some cameras in there and target some sampling, because that would be that would be incredible. I mean, these are just otherworldly habitats. You know, you think about, I'm gonna go dive in Europa's ocean or Titan's ocean. I mean, that's what these places are like.
Except we know that there are fish here. There probably aren't fish on Titan.
Yes.
Probably not.
Yes.
But talk a little bit about how challenging it is for a scientist like yourself to just get access to using a tool like a submersible or even an ROV. It just seems like it's such a daunting process.
It's daunting, and there's such a long lead time. Just as a general example, our work is funded by research agencies, and you might have an idea. You have an idea, say in January of a year. You got to assemble a team of collaborators that can work with you to put this idea together. You write a proposal. Usually you can submit a proposal once or twice a year. There are deadlines, target dates that you submit them to. You submit your proposal. Usually it doesn't get funded on the first go round, but maybe you get funded on the second or third go round. You have to wait a year between submissions. So if it takes 2 submissions, that's essentially 2.5 years from when you had the idea to when your grant gets funded. And then you've got to get your crew scheduled. And there's only one research submersible that's funded by the National Deep Submergence Facility. That's the Alvin. And it can take 3 to 4 years to get an Alvin crew scheduled. So
And if you have bad weather.
oh yeah, and then you have weather and you get thrown off the water. Oh, it's it's essentially a 4 to 5 year proposition between when you have an idea and when you can get out there to do the work. So you have to have this constant stream of projects and ideas, so that you've always got something in the mix, and you've always got something in the queue, and you've always got something pending, so that you can keep you and your group busy. Because if you bring in a PhD student to do a project and then the cruise gets canceled because of weather, or there's an issue with the vehicle or the ship or anything, a PhD student is there for 5 years. I've actually had through the entire course of their thesis, the cruise didn't happen. They basically had to switch projects and do something different because they couldn't get their samples.
Oh, that's so frustrating as heck.
But it's easier if you have a project on Jupiter.
Oh, totally. I mean, it's kind of mind-boggling that NASA, the funding level for NASA to explore, ocean worlds versus the funding level for NSF to explore the actual ocean, and the ocean world analogs that are here under under at the bottom of the sea. I would argue that you need to explore the Jesus out of those, so that you can tune what you're looking for in these extraterrestrials ocean worlds, because we've got this opportunity, and it would teach us so much to do more here. And for those of you who are watching, this is a link to a video that the BBC and OceanX Media did about the brine pools that Sylvia and I visited, and we're both featured in it. And I think this is one of the most amazing videos, because
incredible.
These habitats are really just out of this world.
And I was
the creatures are fantastic.
And I was really thrilled that we were able to build the ABS class camera housings that were able to take those images, because those big cinema cameras, they had to be classed the same way as the submersible, because they were so large that if a camera failure would result in,
if they imploded, the sub might implode.
Yeah, it could damage the sub. So it was a huge engineering project to bring those images back as well.
But I don't know how it could have been more successful, because those are some of the most spectacular footage that I have ever seen.
And experiences that we've
ever. Yes. Do you remember the day that they had the 2 subs down there, and one of them was behind like the brine fog, and it was the most,
it's when that photo,
I'll never forget that. It was
when the Deep Rover was taken.
Yeah.
Yeah.
That's why
I was in the other one watching.
It's why we really love the whole idea of kind of buddy diving the submersible.
Mm-hmm.
And
that needs to happen so much more, because it was just an incredible experience. So I thought to sort of wrap us up, we could talk for a minute about, the role of these background, large time series data sets.
Mhm.
And we've mentioned this before, but it's really amazing that, these are data from the Hawaii Ocean time series, just in the upper water column. And you can see there's just tremendous interannual variability. This is a data set from 1988 to 2005. And we can't really describe this level of variability at any other places in the ocean except these long-term study sites. But really doing this, top to bottom in the Gulf of Mexico is our, challenge. That's what we're trying to do out there, is to get these long-term observatories set up so that we can assess the role of this light versus dark carbon in a system like the Gulf of Mexico.
Absolutely.
You can go to the next one, because this will also help us to sort of understand how the microbes play as sentinels in the ocean, and how poised or not the microbial population in the ocean is to respond to the various challenges of climate change. And this picture and text were taken from a paper that was published in Microbiology, Nature Microbiology, a couple of years ago, as a consensus statement by a lot of leading microbiologists that do ocean science. And it's there's a lot of text on the screen, but really the challenge is to understand how microbes respond to environmental perturbation. And this is just not something that we have a handle on at all. And we need to focus a lot of attention on understanding how microbial populations respond to these multiple stressors.
So, Mandy, I sometimes point out that if you were an evil alien wishing to alter the nature of Earth in ways that would not favor humans or any other form of life, actually, you change the temperature and you change the chemistry, and we're doing both.
Yes.
Doing both. And we don't know what the outcome will be, except that it's probably not going to be good for us.
Yeah. I mean, when you think about the fact that life on Earth has sort of co-evolved over billions of years.
Co-evolved, that's the key.
Yeah, co-evolved. And there's an optimal temperature window. There's an optimal pH window. There's an optimal light window for phototrophs. And we're changing all of these. We're pushing the averages to where they are outside the realm of natural variability. And that's always a challenge for organisms to respond, because they can't evolve.
Or we could go to Mars, right?
Yeah, I mean, I'm always fascinated by these discussions of, we're just going to move to another planet, as if, I mean, I'm waiting for somebody to discover the warp engine, but I don't think it's going to happen tomorrow, or next year for that matter. And we can learn a lot about these extraterrestrial environments by studying environments here on Earth, and many of the environments that are relevant are in the ocean. And again, I'm all for space exploration. I think it's great, but I think there has to be some parity in terms of effort and funding for doing work here in our backyards, because we've got such a tremendous amount of discovery that remains to be made. I mean, when you think about it, hydrothermal vents were discovered in 1977, and then we've discovered different types of hydrothermal ecosystems and different types of cold seep ecosystems. And the more we explore, the more new kinds of environments that we discover. And we're certainly we don't have it all nailed down yet. There's so much more that we need to do. It's really frustrating that it's so hard to get funding to do it.
Yeah.
So why do we want to explore the ocean? Here's a few reasons, right? It's not just about research. It's about innovation. It's about understanding ways that ocean organisms and chemicals can improve human health. It's understanding climate change. It's understanding the energy budgets, ocean health and biological health, and teaching people to care. Engagement and ocean literacy is really, really important. And only 7 reasons. They're just sort of the top 7 lists that I typically give to groups when I talk to them about it.
Yeah, one for every
day. Is there
anything
missing perspective?
Well, just because our life depends on it, that's all.
Yeah.
Yeah.
Our
And I,
existence.
and I know, you're always famously saying, no child should be left dry, but, maybe we have no child should be left clean. Yeah, we need to get out there and like get our hands dirty and
Stir up the
stir up the
microbes.
microbes, find the ones that are in your own yard and appreciate them,
Adopt them.
adopt them.
Make them your very own.
But but it really is all about, to your point, Mandy, what other planet is there like this that we know of that we can reach?
This part
Yeah.
of the universe rocks.
No, I mean, that's the thing. I mean, it's just, it's so intractable to think about settling Mars. I mean, it's just, we have so many problems that we need to be focusing those resources on right now. It boggles the mind. It's arrogant is what it is. It's arrogant. I mean, I would love to be the captain of a starship exploring worlds outside of Earth. However, I will settle for being in a submarine and exploring habitats on this planet, because I think we have a lot more relevant things that we can learn doing that. And there's only so many resources, and I'd rather us focus them on the things that we can actually achieve and do that's going to help us in the short term and the long term.
Yeah.
I think before we go to questions, I want the listeners to appreciate that Mandy Joye has been working through this entire presentation while battling, dare I say, a round of COVID. You are amazing. I would be flat out, and you probably should be, but
I probably should be. Thank God for Ricola cough drops is all I can say.
but you're toughing it out.
Yeah.
Just as you toughed it out during that opposition that you faced and the criticism that you got through post Deepwater Horizon, and people who don't want to know the truth. Well, I think people should know the truth that you're suffering right now, and yet you've been just carrying on no matter what.
This is important to me, and I think I really value you and Liz and what you do. And I think it's so important. And, a little virus is annoying. But the problems that we face are so much bigger than that,
Yeah.
I mean, sometimes you just have to suck it up a little bit. Yeah.
You're questioning yourself in the basement. Your kids are upstairs. They
You're staying hydrated.
They've been bringing me cough drops.
Yeah. You're
dropping your cough drops.
Dropping cough drops in, and helping support the good
microbes.
The good microbes that are going to help you get better.
Right. But thank you.
My pleasure.
You to put up with a few questions?
Sure.
Let's see what we've got here. All right. Yeah, so you can put questions right up in the Q&A box. And Grant is just thanking us for the amazing and tragic presentation, and to talk about such an underreported topic in this important area. And I agree, it is really very underreported, and we've got lots of work to do. I think starting right in school, with the kids, it's like down to the three R's, right? But we really need to put the big N, nature, on the curriculum starting early on.
Or the big M, microbes.
Microbes.
Yes.
Or the big B, biogeochemistry.
I think we need earth and ocean science taught starting in middle school to everybody. And we do an ocean camp for middle schoolers here at the university, and there's always a wait list. We've the past few years, we've had to increase the number of sessions because there's so much demand, and we offer scholarships. And I think this is a real way to get kids jazzed about the ocean at the point where they're deciding, what am I going to do? What am I interested in? What do I want to do?
Mm-hmm.
And I think that's really important to engage them and be there, be a resource for them,
Yeah. We've got a couple questions here. Elva's asking, sincere congratulations to Mandy on this great talk. Wonder if promoting Deep Ocean Observatory in the Gulf of Mexico could benefit our long-term knowledge and go on to understanding resilience.
Yeah, I mean, that's one of the big goals of what we're trying to do. And I'd love to tell you more about this sometime, because there's this field of ecology called biocomplexity. And biocomplexity has been pursued primarily in terrestrial ecosystems because the ocean is complicated and the physics are mind-bending. But when you put together a team of physicists and chemists and biologists and these complexity modelers, and you think about the kinds of data that you need to really enable these large biocomplexity efforts, it is at the scale of a large institute. But what you can start to do is really, if you tune the model to the system, then you can perturb the model mathematically and see how the biology responds. And then you can test and see from your field data if the model's giving you reliable information. Is the model predicting how the microbial food web is shifted and how that shift propagates up through zooplankton and fish? And there's not data anywhere that describes that sort of thing. Nowhere. It's just not available, because people work on myctophids, or they work on zooplankton, or they work on prochlorococcus. They don't work on all of it together. Right. And the key is really to understand resilience and response to perturbations and timescales of perturbation, because Deepwater Horizon taught us that the timescales of these perturbations are much longer than we anticipated. It's not a couple of months or a year, it's multiple years. And for most of the biological compartments, from microbes up to the myctophids, it was 3 to 4 years. And in some cases, 5 years.
Yeah.
So,
and some probably still ongoing,
Yeah. Yeah. So. Oh, yeah. I mean, certainly some of them are still ongoing.
All right. Another question is asking, is it safe to swim in the Gulf of Mexico?
It is safe to swim in the Gulf of Mexico. The one thing that I would caution is that there are still some layers of buried oil on beaches. So if you dig a hole on the beach, make sure there's no residual. I mean, you can see the hydrocarbons in rainbow sheen. So yeah, don't sit in a hole that has rainbow sheen, but in general, the Gulf is fine.
Yeah, it really does persist in the sediments and the soils. Yep, and
it does.
An open Prince William Sound where the Exxon Valdez ran aground, you can still pull back the pebbles, the beach pebbles, and still find oil there.
And it's pretty pristine, right? I mean, it's just like, it looks like it was deposited yesterday. Yeah. That's how it is in Barataria Bay. That's why the dolphins are suffering still, because it's just wicking out of the salt marshes.
Yeah, it will be for a while, but I think overall swimming is fine. See, Jack is asking, when is the camp for middle schoolers at the university?
This year there are 2 sessions in June. I can send the dates for you, but if you go to the UGA Summer Academy website and search for Ocean Discovery Camp, you'll find the dates.
Great. I want to respect Mandy's need to rest.
Yes.
But if you want to know a bit more, check out the new Ocean Odyssey book that features, ta-da,
here, let me help you,
Mandy Joye talking about biogeochemistry
in action.
Awesome.
With a nice little profile and a follow-up of our great conversation today.
Awesome.
Really appreciate it, Mandy.
Thank you both for inviting me. It was great.
Yeah, it's so good.
Despite
to see
COVID, I'm happy that I did.
Know, right? We got to get you out there. We got to get around to getting some subs and an ROV there that can be there for you all the time.
And I like the observatory idea. I love that. I think we should co-conspire and see what we can do.
Yeah,
let's do that.
At DOER, we put a lot of support into the Station Aloha observing system, out in Hawaii, and it's in like 4,000 meters. So it's safe from trawlers and things.
Yeah.
I think we could do the same thing there. If we can just get
we should talk about it, because we'll know soon whether this is actually going to fly. And if it does, I think we can do some really amazing stuff.
Yeah, I'd love it if we could have the Mandy ROV.
There you
Oh.
go.
On demand, on demandy. Get you out there,
good.
whatever you need to do. So, well, before we close today, I want to say, and Sylvia would like to say thank you to everyone and to our producer, Ocean Elders.
Yes.
We're
Behind
so
the
grateful.
Curtain. Behind the curtain is
Yes.
Gigi Brisson.
Yes, she's like the levers.
Yeah.
We really appreciate all of you who join us each and every time and keep coming back. Water connects us all, and we're so grateful to you. And until next time, remember,
You must protect the ocean as if
your life depends on it
Because-
As it
it
does.
all right, thank you, everyone. We'll see you next time. Mandy, get
Thank
some
y'all.
rest.
I will.
Hydro-
Take care. Bye.
All right, bye. Bye for now.